Welcome to today's Explainer. Let's jump right in and build a foundational understanding of our Earth's climate system. We all talk about the weather, and we constantly hear about climate change. But to truly grasp the dramatic flux of global warming that's happening right now, we first have to understand the baseline. Like, how do we even define a climate in the first place? Today, we're going to explore the brilliant system used to map out the world's climates, and then we'll uncover the mechanics behind how and why those very maps are changing today. We've got a fantastic roadmap for this. We'll start with decoding world climates and Köppen's 5 climate groups, then shift gears into the reality of climate change, the mechanics inside the greenhouse effect, and finally wrap up with global warming and our future. All right, Section 1, Decoding World Climates. Let's look at empirical versus genetic classification. So to get our scientific baseline, we really have to ask, how do researchers actually organize something as impossibly massive as global weather patterns? Well, broadly speaking, scientists use two different approaches. A genetic classification tries to organize climates based on their underlying causes. But the crucial point here is that the most widely used system in the world, which was created by a scientist named V. Köppen way back in 1918, is actually an empirical one. That means it's strictly based on hard, observed data. We're talking specifically about mean annual and monthly temperature and precipitation. Köppen noticed a very close relationship between the distribution of vegetation and climate, and he used these hard numbers to draw the boundaries. Moving right along to Section 2, Köppen's 5 climate groups, which is basically the alphabet of our atmosphere. What is truly fascinating is how Köppen took all that complex temperature and rainfall data and boiled it down into a remarkably simple alphabet system to categorize the entire planet. He created 5 major climate groups, A through E, and they are neatly defined. Group A is tropical, where the average temperature of the coldest month never drops below 18 degrees Celsius. C is warm temperate, D is cold snow forest, and E is the polar or cold climate, where even the warmest months stay below 10 degrees. Now, 4 of these groups are based purely on temperature thresholds, but Group B is a little different. You might have noticed a pattern. Groups A, C, D, and E all represent varying degrees of humid climates, ranging all the way from the sweltering tropics to the freezing poles. They stand in stark contrast to Group B, the dry climates. Group B is the only major group defined not strictly by temperature, but by moisture. Specifically, it's where potential evaporation simply outpaces rainfall, leaving the landscape arid. Of course, the real world is way too complex for just 5 buckets. So Köppen added lowercase letters to these capital groups to account for specific seasonal shifts. For example, adding an F means there is no dry season at all, while an M designates a monsoon climate with a short dry season. For the dry B climates, he used capital letters, like S for a semi-arid steppe and W for true deserts. It's an incredibly elegant way to literally read the atmosphere just by looking at a few letters. Which brings us to Section 3, the reality of climate change. What happens when a map shifts? Okay, so we've mapped out this beautifully organized world using Köppen's scheme. But what happens when these established, neatly categorized climate zones start to experience dramatic, undeniable shifts? First, we have to acknowledge that variability is completely baked into the Earth's history. Geological climate change is a totally natural, continuous process. I mean, look at the timeline. 500 to 300 million years ago, during the Cambrian period, the Earth was remarkably warm. Then we had the Pleistocene epoch, with massive glacial periods peaking about 18,000 years ago. Even in recent human history, Europe experienced a little ice age between 1550 and 1850. The climate has always fluctuated through natural cycles of warming and cooling. But, and this is a massive but, what we are seeing today is altogether different in both its speed and its cause. Headlines have been warning of rapidly retreating Himalayan glaciers. We're seeing the shrinking of the Gangotri Glacier at an average rate of 23 meters per year. That is not a slow geological epoch shifting. That is an urgent, modern reality tied directly to an alarming rise in greenhouse gases. So why is this happening? Let's dive into Section 4, Inside the Greenhouse Effect and the Mechanics of Warming. To really grasp why these massive glaciers are melting at such unprecedented rates, we have to look at the exact mechanics of what is actually happening in the atmosphere to drive this change. And the best way to grasp this is through a simple, everyday experience, the hot car analogy. Think about a closed car sitting in a parking lot under the glaring summer sun. The glass windows are transparent to the incoming shortwave solar radiation. The sunlight streams right in. But that same glass is opaque to the outgoing long-wave heat radiation trying to escape. The heat gets trapped, making the inside of the car much hotter than the outside air. Well, that is exactly how our atmosphere is currently behaving. Taking this to a planetary scale, it happens step by step. First, our atmosphere allows shortwave solar radiation from the sun to pass straight through and strike the Earth. Second, the Earth's surface absorbs this energy and emits it back upwards as long-wave radiation. Third, certain gases in our atmosphere act just like the glass in that hot car. They absorb that outgoing long-wave radiation. And finally, this trapped energy warms the entire lower atmosphere. So what exactly is our atmospheric glass made of? Well, carbon dioxide is the largest culprit in terms of concentration, largely due to fossil fuel combustion and deforestation. And get this, it's rising by about 0.5% every single year. We also have chlorofluorocarbons, or CFCs, which are highly effective at trapping heat and, as a terrible bonus, destroy the protective ozone layer in the stratosphere. Then you have methane, nitrous oxide, and ozone in the lower atmosphere. The more of these gases we add, the thicker the glass on our planetary greenhouse becomes. This leads us to our final section, Part 5, Global Warming and Our Future. Let's talk about the stakes. Now that we understand the mechanics of how heat gets trapped, let's look at the hard data on how much the planet has actually warmed up and what that means for us. To set our baseline, the annual average near-surface air temperature of the entire world is approximately 14 degrees Celsius. That is the global thermostat setting that has historically allowed human civilization and all of Köppen's climate zones to thrive. But we are turning that global thermostat up. By the end of the 20th century, the globally averaged annual mean temperature had risen by 0.6 degrees Celsius compared to the end of the 19th century. Now, 0.6 degrees might sound like a tiny number to you and me, but on a planetary scale, a 0.6 degree shift is a massive, incredibly disruptive injection of heat energy into our weather systems. And here is a frankly staggering statistic that highlights how fast this is accelerating. The 7 warmest years between 1856 and 2000 were all recorded in the final decade of that period. Furthermore, the year 1998 was likely the warmest year not just of the 20th century, but of the entire millennium. The data is pointing in a very clear, very warm direction. In response to these stark numbers and the looming threat of rising sea levels and shifting climate zones, the international community realized they had to act. Efforts like the Kyoto Protocol, which was proclaimed in 1997 and went into effect in 2005, represent major global attempts to control these emissions. It was ratified by 141 nations and legally bound 35 industrialized countries to reduce their emissions to 5% below 1990 levels by the year 2012. It was a crucial, massive first step in trying to arrest the trend of global warming. As we wrap up this explainer, it's wild to think we started with Köppen's neat, orderly climate letters and ended up in today's chaotic warming reality. If global warming continues at this pace, reversing it will be incredibly difficult, and those reliable Köppen climate zones will shift uncontrollably. So I want to leave you with this critical question to think about. Will the world community rise to this challenge and adopt a lifestyle that leaves behind a livable, stable world for the generations to come? Thank you so much for joining me today, and keep exploring.